Okay, just running over the answers to a couple of the Chatelier questions from the Chapter 8 textbook review. Question 20 asks us to analyse one of the industrial situations. Now, what we're doing here is using carbon monoxide as a fuel in order to generate energy. So, as it says, it is an exothermic reaction. Delta H is negative. And we're going to look at what happens if we change the conditions. Now, it's an exothermic reaction, so that means as reaction goes forward, it wants to release energy. An exothermic reaction, as it goes in the forward direction, it releases energy. Now, any reversible reaction certainly, if the forward reaction is exothermic, then the reverse reaction is always endothermic. So we can turn an exothermic reaction into an endothermic reaction simply by sending it the other way. So in this case, if we were turning carbon dioxide back into carbon monoxide, it would be an endothermic reaction. What we're talking about here is the forward reaction, so we describe it as being exothermic. Endothermic reactions, of course, consume energy. Now, what's going to happen to the equilibrium if we do something? Well, if we decrease the temperature, the reaction's going to want to do the opposite. So if we decrease it, it's going to want to move in the direction that increases the temperature. And increasing the temperature, of course, is what an exothermic reaction does. So if the temperature goes down, then the reaction is always going to go in the exothermic direction, because that means the temperature goes up. And in this case, the exothermic direction is the forward direction to the right, however you want to describe it. Equilibrium position in terms of adding a catalyst, no effect. It will simply reach, if the system is already at equilibrium, it'll have absolutely no effect. If the system's not at equilibrium, it will reach equilibrium more rapidly. If we want to add a reactant, then the reaction's going to want to get rid of that reactant, so it's going to move to the right to remove oxygen. Part B, what happens to the equilibrium constant as a result of all these changes? The only thing that has an effect on the equilibrium constant in terms of the Le Chatelier change, the only thing that affects K is temperature. So that means if the reaction is going forward in A, K will increase. Every time a reaction goes forward, you get more products. The numerator is higher than the denominator, so therefore the value of the fraction increases. 2 and 3 are no change. Don't involve a change in temperature, so don't involve a change in the equilibrium constant. Okay, part C, if carbon monoxide is any use as a fuel, that means when you react it, you're going to be getting a lot of energy produced. that means all the carbon monoxide, or a huge amount of the carbon monoxide, must react. Therefore, you must have a high equilibrium constant. K must be high. Forgive my writing. As most CO needs to react for it to be useful. That's question 20. Question 25 starts off by looking at rate, then looks at equilibrium, sees if there's any difference between the requirements for each of those. So to get a rapid rate, we need to maximise rate. What we need is frequent collisions that break bonds. That's the essential requirement for a rapid rate. And that always means high temperature. Increasing the proportion of collisions with sufficient energy to break bonds, overcome the activation energy barrier. And high pressure. You get the particles closer together, they're more likely to collide. For equilibrium, on the other hand, it's going to depend on the equation. A high yield depends on whether it's exothermic or endothermic. So the reaction itself is exothermic. So that means the reaction releases energy as it goes to the right. The environment gets hotter as it goes to the right. So if we want to get it going to the right, we need to do the opposite. If we want to encourage it that way, we need to do the opposite. So we need to remove energy. So lower the temperature. So always think about that sort of opposition. If it wants to do one thing, we want to do the other. We want to encourage it to do that, we need to do the opposite. For pressure, we want it to move to the side with fewer particles. So high pressure will encourage it that way because it will want to reduce the pressure by going to the side with fewer particles. So what we see is high pressure, excuse me, high pressure is good for rate, good for equilibrium. No problem there. But we see that temperature, we need a high temperature for rate, but a low temperature for equilibrium yield. The classic compromise there is solved by using a catalyst. That enables That gives you a reasonable rate. Spell would be good. Economic rate at a temperature low enough to give a decent yield. The classic way of overcoming that compromise in temperature.